is very well positioned to talk about this because his group at Princeton has been doing a tremendous amount of work over the last few years on building good programming models that have sound semantic foundations for programming these very complicated hardware and software systems that run our modern internet networks. Cole is a grad student at Princeton and is aiming to graduate at the end of the year, so I'm sure he'll be keen to talk to many of you. And I will leave him to tell you about Concurrent NetCore. As soon as the slides work.
As soon as the slides work.
The second option right on the
second option, right? Okay,
there you go.
View full screen mode.
Thank you. Okay, how's the mic? Great. So thanks, Anil. Now for something completely different, which even includes clickers. Sorry for the slow setup time. Okay, so as a backstory, my laptop doesn't display on this projector, so I had to borrow one.
Press the red button.
Just close the window.
Okay, great. Thanks. Okay, so today I'll be talking about a policy language for describing not only the packet processing behavior in software-defined networks, but also the packet processing pipelines in switch hardware that enacts those network policies. So this is joint work with Michael Greenberg and my advisor, Dave Walker. So quick review on networking. Suppose we have a small network. Let's say this is an enterprise network with a set of hosts connected by one or more switches, maybe connected to the internet. And in a traditional network, each of the switches will be running a distributed protocol for communicating global state of the network. We're doing things like, say, using OSPF to calculate shortest path routes. In a software-defined network, those distributed protocols are replaced with a centralized controller, which is a program running on a server that has a connection to each of the switches. And so instead of running distributed protocols, the controller simply tells the switches, here are the rules that you should use to process packets. And so the most popular and widely deployed protocol for doing that installation is the Openflow 1.0 protocol, which gives the controller the abstraction of switches as a single large table. It's a table of prioritized rules, where each rule is a combination of a predicate, which matches on potentially any of the fields in a packet header, and some set of or some listed actions, which could potentially modify any of the fields, duplicate the packet, and of course forward it or drop it. So the problem is that switch hardware isn't quite that simple, and there are a couple things going on under the hood. So one is that there isn't just a single table. There are many different tables, and each table tends to have a specific purpose for processing particular parts of the field. So for example, there might be a dedicated L2 table that just reads the destination MAC, or there may be a special table for only pushing and popping VLAN tags. And so in Openflow switches today, if you were going to take a legacy switch and convert it to Openflow, typically what you do is to pick a single table, which is very small and only one point in the pipeline that supports all of the Openflow operations, and then you leave the rest of the pipeline unused. At the same time, there are new architectures coming out with reconfigurable pipelines. In terms of reconfigurability, each of the tables in the pipelines can be configured to match different fields in the packet header. And the choice of fields changes the characteristics of the table. There's a fixed amount of area, and so if you choose to match more fields, there are fewer rows available in that table for installing your rules. So the current version of Openflow doesn't allow you to any insight into this sort of piece of the hardware. As a result, there's been a recent proposal in the SDN community to move to a so-called Openflow 2.0 version, which splits the interaction with the controller with the switches into two phases. In the first phase, the controller installs a table configuration that sets up that pipeline, and then in the second phase, actually populates the rules, the tables with rules that govern the network behavior. And so phase one happens at sort of the setup of the network. It's akin to flashing an FPGA, and so at least as of now, it's not something you can do while the network is running. So phase one, set up the network, set up all the pipelines and all the switches. Phase two, populate the tables. Okay, so this is sort of the broad SDN world at this point, or at least one part of it. So what have we done? So first, we've developed a core calculus that describes both the packet processing policies for phase 2, but also the switch pipelines for configuring tables in switch 1. The core calculus comes equipped with a type system, both denotational and operational models, meta-theoretical properties, and reasoning principles for program transformations. We've also modeled 3 existing switch architectures in terms of the pipelines that they use. And finally, the controller quite often will connect to many different switches in the network. So rather than writing a different policy for every switch, it's convenient for the controller to use or to define a virtual pipeline that represents its sort of minimum processing requirements for a network operation. And so we've developed a compiler that takes this virtual pipeline and maps it down to physical pipelines, and also generates a transformer that keeps track of when population time rules are installed into tables in the virtual pipeline, they then get mapped down to the physical pipeline. Okay, so I'm going to introduce the language by showing 2 fragments of actual packet processing pipelines in real switches. So the first is the Broadcom Trident switch, which is a fixed packet processing pipeline. There are 4 tables, and each table can read and write to a fixed set of packet fields. So intuitively, you can think of both the entire pipeline and also each individual element as a function from packets to sets of packets. So if the pipeline receives a packet and then produces the empty set, that indicates the policy is to drop the packet. If it produces the singleton set, possibly with some modifications to fields in the packet, that means the packet's just being forwarded on out some other port. And if it produces a set with many packets, that indicates some kind of packet duplication for flooding, broadcast, multicast, something along those lines. So the first element of our language is a way to describe tables. There are 3 pieces here. The first is a table variable name, so we'll call the first table W. And the second is a type annotation, which is a pair of sets of fields. The first set of fields are the fields that policies installed later into this table are able to able to read. The second set is the set of fields able to write. We also have a sequencing operator. So again, if you think of these as functions from packets to sets of packets, sequencing runs the packet through the first element and then applies the second function to each of the packets that are in the first resulting set. And of course, we can also use, we can give a table name to our second table. In this case, it's a table that does L2 destination MAC address routing. And so the third table is an optional table for doing multipath. And so if the first table configures a bit of metadata that indicates that we should be doing multipath routing, then the packet should be processed by this table Y, otherwise nothing should happen. And so we have if statements over predicates, and predicates are form a Boolean algebra over sort of atomic tests on fields. In this case, it's does the vport field equal 1? And I should mention the vport field here is a bit of metadata that exists on the switch, but doesn't leave the switch, so it doesn't actually get pushed into the packet header. And so finally, the results of both of the branches, or either branch rather, are fed into the final table, which in this case can read or write any field. And this is useful for doing things like pushing and popping VLANs and so on. Okay, so for the second pipeline, the first was the Trident switch is a fixed pipeline, whereas Intel's FlexPipe architecture supports reconfigurability. And so there are 2 differences here. The first is that in the first 3 tables, each table is capable of being configured to read any 36 bits of the packet header field. And it can be configured to write to any of the fields. And so this is really, the way we model this is using a family of policies that describe each configuration that the pipeline can take on. So I've picked one as an example. We'll say that W is the first table. It can match on the type field, which is sort of pseudocode for is the packet SSH or is it UDP or whatever. And it can set a bit of metadata. So the second difference is that the FlexPipe supports concurrency. That as packets depart from the first table, there's a fixed but reconfigurable split of packet fields, so that a packet with 10 fields might be split into 2 packets with 2 sub-packets with 5 fields, and the 2 tables on top and bottom in the middle concurrently access the packet and write or read to those fields. And so we introduce a concurrency operator to model this, which is the bar operator that's annotated by the field split. So the subscript X are the fields that the left-hand side is allowed to write, and the subscript Y similarly is on the right. And so after the packet has been processed by either side, the fields are then recombined, and in this case, processed by a final table, which we'll call C. Okay, so this is sort of a sense of what packet processing pipelines look like and how we model them. But what about the controller? So like I mentioned earlier, it's quite common for the controller to connect to many different kinds of switches in the network. And so it's convenient, rather than rewriting your policy for each different packet processing pipeline, to instead, for the switch, or for the programmer at the controller to define a virtual pipeline that expresses sort of the minimum functionality that the controller is going to need as the network runs. So here's an example of such a pipeline. Let's say that the application we'd like to implement is a combination of monitoring and routing. That for SSH traffic, we'd like to siphon it off and copy SSH packets off a special port to be sent to a server for further security analysis. At the same time, we'd like to do sort of layer 2 routing based on destination MAC address. So we're using a new operator here, which is the union or packet duplication operator. Intuitively, this is if we're talking about functions for packets. So sets of packets, the semantics is copy the packet, run it through both sides, and take the union of the resulting sets. And of course, we need packet duplication here because we'd like to do routing as normal, but copy some sets of packet, or some packets, that is SSH packets, to send off for analysis. So this gets passed off to a compiler, which fits it to table pipelines in hardware, and also produces a transformer, so that as the controller in the second phase installs rules that actually govern which packets get shunted in which direction, and how routing works, those get mapped as well to the appropriate physical tables. So here's an example monitoring policy. If the type of traffic is SSH, send it out to special port 1, otherwise drop the packet. And here's a sample, albeit really boring, routing policy. It just does layer 2 MAC routing. So if the destination MAC is 1, send it out port 2. If it's 2, send it out port 3. And as more hosts join and leave the network, the controller is going to update this table to reflect the locations of the hosts. Okay, so the controller conceptually installs these in the virtual pipeline. In reality, they go through the transformer and get mapped down into the tables in the physical hardware. So as part of this work, we developed a targeted compilation algorithm for the Barefoot Network's RMT switch. But in doing so, we developed 3 techniques that are useful for overcoming constraints in physical pipelines that should be useful across many different pipelines. And so I'll go through these briefly now, although I won't have time to dive into great detail. I encourage you to read the paper. So the first constraint is that physical pipelines don't allow for arbitrary packet duplication. There's generally a hardware element that will do that duplication at a particular point in the pipeline, although it tends to be a different point in each of the switch architectures. The second point is that, similarly, not all elements support writing to all fields. So the RMT architecture in particular requires that all of the port fields, or all of the output ports, be decided at the time of packet duplication. And so it's necessary to migrate and consolidate that decision to a different point in the pipeline if it was going to be made later. And finally, at the end of this, we have a bunch of tables, virtual tables, and we have a bunch of physical tables, and we need to figure out how to put the virtual tables into the physical tables. So briefly going through these. The first 2 passes rely on introducing additional metadata on the switch to account for decisions that would have been made in the virtual sense. So, for example, if we're taking the union of P and Q, 2 sort of arbitrary policies, our goal is to extract out the packet duplication. And so we do that into this first stage, where we set a new bit of metadata, which we'll call F, with a unique tag for each packet copy. So first the packet is copied, tagged, and then the remaining policies are arranged in a sequential pipeline where each stage is wrapped with a predicate checking the metadata. Right? So if the metadata indicates that this packet would originally have been processed by policy P, P gets applied later in the pipeline. If not, the packet gets passed through the pipeline unchanged. Similarly, suppose we wanted to migrate the port modification in front of some arbitrary policy P. So we can't do this naively. Basically because of something like data dependencies, that there may be predicates in P that depend on the old value of the port. And similarly, there may be writes to the port field that would later be overwritten by this assignment of 1. So there's sort of a two-stage analysis here. First, we analyze P to figure out sort of the conditions under which the modification would take place. And then we extract that at the beginning and set a bit of metadata to indicate the fact that this decision took place. Then we modify the policy P to, instead of predicating on the original port, to predicate on this additional bit of metadata, and also to sort of remove modifications that would have happened. Okay, so at the end of the first two phases, what we're left with is some sequence of tables, either joined sequentially or with concurrency. And we also have some set of physical tables that we'd like to place these tables onto. Right, so each table has some estimated size in terms of the number of rules that are going to be installed into it, and we're trying to fit these. And so there are some decisions to be made. For example, there's sort of associativity, which is, do we put the first two virtual tables into the first single physical table, or maybe just the first one into the first one and the second one into the second? Similarly, concurrency commutes. And so we can also choose to swap out, not swap out, but swap the concurrency, the sequence, or the ordering of these tables. So we've developed an algorithm to do this. It's a combination of brute force and dynamic programming. The brute force is basically to try all combinations, or rather all alternations of the ordering of concurrency. And it's possible to do this because in most of these programs, the number of tables is not actually that great. And then we use dynamic programming once we're given a sequence of tables to do the final fitting. And one thing to note is that each of these passes also produces, or also does a refactoring of the virtual pipeline. And so later, when the controller goes to install a rule at population time, it's important to remember that mapping. And so each pass generates a transformer that takes a rule from the controller going to a virtual table and places it in the appropriate physical table. Okay, so I've talked a little bit about the syntax of this language by example. Here it is all in one place. Predicates form a Boolean algebra. The basic test is a test on fields. Does this field equal this particular value? Policies are predicates, modifications, tables, union, sequencing, and concurrent composition. This is drawn heavily from the frenetic language of languages, frenetic family of languages, rather, that govern or are used for configuring the behavior of global or of software-defined networks in the whole. The main difference here is that we're also interested in the physical hardware of the pipelines on the switches, and so we introduce table elements and concurrent composition. We also introduce a small step operational semantics, whereas previous models had used a denotational semantics, and we introduce a type system. And there's one other point, which is that by adding concurrency, now things can go wrong. In particular, we can have race conditions where two different tables try to read and write the same fields. This, of course, makes no sense in hardware. So the typing judgment is designed specifically to alleviate concurrency issues. A policy P is well typed at a pair of sets of fields, one of which are the read permissions, the other the read and write permissions. And so here are a couple examples of well-typed policies. Predicates are well typed at the port field, the fields they read. Modification policies are well typed at the fields they modify. Tables are well typed at their typing annotation. And concurrency is well typed at a pointwise union of the read and write fields, subject to a set of constraints that preclude read-write conflicts. Okay, so properties of the language. There are a couple technical things I haven't presented on the slides, but I'll go through in the definition of normalization. So the first is that we have a well-formatted thing. Well-formatted is condition on types, which is that the read and write sets can't intersect. The second is, so the read and read-write sets can't intersect. The second is that the set of packets that are going to be processed by the policy are well typed at a type if the packets all include at least the fields that the type talks about. Okay, so if those two conditions are true, and the policy is well typed, then the policy will eventually step via the small step operational semantics to the identity policy, producing an output set of packets pk prime, and two things will hold. The first is that pk prime, all of the packets within it will be well typed at the type tau. And second, if you look at the non-writable fields for every packet in that set, none of them will have changed, which is what you would expect. Non-writable fields aren't written to. We've also grouped confluence. So again, operating over packet states. if sigma steps to sigma 1 and sigma also steps to sigma 2, then there exists some other sigma prime such that sigma 1 and sigma 2 both step to sigma prime. And so together, normalization and confluence give us strong normalization, which is that for all well-typed policies and all well-typed packet sets, the policy produces a unique packet set. And this is kind of what you would expect for an actual switch. We want these things to be deterministic, and if they didn't, or if they weren't, that would be something that would be cause for alarm, perhaps. The third thing we proved is a relationship between the small step semantics and the denotational semantics I've alluded to earlier, which is functions from packets to sets of packets. In particular, if you set aside concurrency for a moment, we've shown that our small step operational semantics coincides with a fragment of the NetCAD language, which is a language for discussing, for programming SDN policies at the controller level that conveniently comes equipped with an equational theory for reasoning about program transformations. And so this gives us access to that equational theory. We've also proved additional equations, specifically regarding concurrency. And this isn't complete, but given a well-typed concurrent policy, you can choose a sequential ordering. And we've used this to prove that our compiler passes are correct. Okay, so wrapping up, we've developed a core calculus for not only talking about packet processing, but also packet processing pipelines. We've modeled real switches, and we've designed compilation algorithms that translate from one to the other. So what's the next step? Well, we're currently playing a game I like to call convincing vendors to give us access to their low-level proprietary APIs, which is actually going reasonably okay, I hope. But the next step is to implement the compiler and the transformer on a real chipset. So, thanks.
Do you have any questions?
Jonathan Kimmington, the Rusty University. I was just wondering, does your system support encryption of the packets inside the network?
No, it doesn't. So encryption would be an additional action that the language would be able to take. I'm assuming you're talking about encryption, sort of in-switch encryption, not sort of sending it to a middle box and doing encryption there.
I'm talking about IPsec, where you use low-level UDP.
So, yes and no. I mean, you could think of that as sort of an atomic action. And so, just as we have modification, you could think of this as additional modification with additional constraints. But I don't think it's been fully worked out.
Gabriel Scherer from INRIA. Something I did not fully understand during the talk is you seem to compile away parallelism at some point with your plus construction when you compile that to the sequential. Do you actually rebuild some parallelism after the fact in the dynamic programming algorithm?
So the plus operator isn't quite parallelism. It's more of a duplication operation. But the parallelism is implicit, so it doesn't go away. It just gets placed in a different place. And so the semantics of packet duplication are that when you duplicate the packets, both packets are then sequentially processed by the remaining pipeline. And the architecture will pick some non-deterministic ordering in terms of which packet gets processed first.
Yeah, I think let's thanks Cole for a great talk. We're going to have a brief 10-minute break. We're just a few minutes behind schedule. If the speakers for the next session could